To scale autonomous LLM agents so they can run continuous tasks without failing, the architecture has to be flawless. Most developers start by feeding the model a static megaprompt and trapping it in a simple input-output loop. The volume of unfiltered data flowing through this loop builds up until the system inevitably shatters under the load. Every turn in the conversation forces the model to reprocess the entire historical transcript, causing token costs to multiply exponentially. This expanding block of redundant context rapidly consumes the available quota, triggering API rate limits that paralyze the application. Relying on passive memory management and a static context window guarantees that any complex agent architecture will break under load. To fix this, we have to isolate the latency. In long-running agentic loops, the primary bottleneck is time to first token. We bypass this delay using key-value, or KV, prompt caching. This method saves the underlying state of common prompt sections, shifting the compute burden away from active processing. This dashboard shows active compute tokens shrinking down. Converting repeated inputs into key-value cache blocks skips the initial inference phase. Bypassing this processing gives a 90% discount on input costs. Plus, cache tokens bypass API rate limits, keeping the loop moving. Developers can accelerate this setup by prompting Claude Code to inject cache control markers, optimizing the cache hit rate. Offloading static data directly to the cache drops system latency and turns a financially impossible continuous loop into a viable architecture. Another common error is hard-coding hundreds of complex tool schemas directly into the initial system prompt. Dumping that much static data upfront clogs the context window, leaving the model with a restricted environment that degrades its reasoning capacity until it is wiped clean. Instead, we use a tool search tool. This acts as an external repository, safely outside the active context window. When the model needs a capability, only the exact required JSON schema drops into the active space. This technique is called defer loading. It relies on the speed of just-in-time tool declaration rather than upfront bloat. Loading tools dynamically preserves the context space, giving the model the room it needs to execute complex reasoning. Even with tools loaded efficiently, external APIs will frequently return massive raw JSON payloads. Letting external tools dump unfiltered responses directly into the prompt exhausts the token limit. We prevent this using programmatic tool calling. The model pauses to write a Python script that inspects the incoming payload schema first. It then writes a follow-up script to surgically extract only the required data point, passing a tiny, precise payload forward. The model leverages its native coding capabilities to act as its own data filter. Building this programmatic extraction layer ensures that only strictly necessary bytes consume your token limits. Over time, even a highly optimized continuous loop will accumulate enough transcript history to approach its maximum context threshold. Before the system hits that limit, execution is paused. The entire sequence of older conversation terms is routed away from the main thread and sent to a separate summarization model call. This secondary node processes the unused history, compacting it down into a short, dense summary block. This compacted summary seamlessly replaces the sprawling history in the main execution loop. Compaction functions as a pressure release valve. It frees up context space and keeps the model on track without losing the historical thread. With the data flow controlled, the next factor is cost. Running a heavyweight model on every single turn of a continuous loop is financially inefficient. This orchestration map shows the advisor strategy, a method for decoupling high-level intelligence from standard operations. A smaller model, like Sonnet, acts as the primary executor. It handles the rapid loops, standard coding, and tool calling, keeping the baseline operational costs low. When the executor hits an odd or high-impact edge case, an escalation protocol triggers an advisor call, routing the transcript up to a larger model like Opus. Opus reviews the issue and issues a specific directive back down to the executor to resolve it. To secure this architecture, Workload Identity Federation, or WIF, is implemented to eliminate the risks of static API keys, while the Anthropic CLI manages console operations. Dynamic routing between specialized models ensures you pay for Opus-level intelligence exactly when the task demands it, and never when it doesn't. When these components are assembled, the system functions as a cohesive agentic architecture. Key value caching accelerates start times. Dynamic tool search and Python extraction protect context windows from bloat. Memory compaction prevents overwhelming the system. The model actively manages its own state and memory across every loop, shifting away from a reliance on external prompt management. To achieve true autonomous scale requires systems that lock together with perfect dynamic synchronization and rigorous data constraint. Proactive context engineering provides the stability required to operate Anthropic agents at an autonomous scale.